block model.
Thanks, Avi and Ran, for the invitation. Okay. So, in fact, I'll tell you about the stochastic block model, and most of the work is with my student Colin. Outstanding student finishing this year at Princeton, his PhD. So I'll start with the model. So the notation I use is SBM and with 3 parameters. Okay, so the first parameter is going to be an integer, is the number of vertices. So what is the stochastic block model? It's going to be a random graph which has some clusters. Okay, so when you talk about drawing element from the block model, what you really draw is 2 things. It's first a partition of the vertices, I'll define this in a second, and then the graph together. So it's 2 objects. So n is going to be the number of vertices in the graph. P is going to be a probability vector of dimension k. And k is the number of communities or clusters. So these are positive numbers that add up to 1, probability vector. So what's happening here is that you start with n nodes, and for every node, that's what the vector is, x, which is x1, x2, xn, this is going to have IID component under this probability distribution P. So you color every node with one of the k colors, and color j comes out with probability pj. So roughly your groups, you roughly have k groups of size np1 for the first group, np2, and np3 in expectation. There's some fluctuation. So now that's the second parameter, and the third parameter here, w, that's going to be a k by k matrix. So it belongs to 0, 1 to the power k. These are numbers between 0 and 1, and it's a symmetric matrix. And these are governing with what probability you connect 2 nodes depending on their colors. So if you are in group 1 and 2, if you take a node in group 1 and 1 and 2, you connect them with probability W12. If you are in 1, 1, you connect with W11, W2, 3, etc. Okay. And you put the edges independently, conditionally on those labels. So it's basically putting an Herder-Schwenny graph here of parameter W11, another one here, and then a bipartite Herder-Schwenny between any of these groups. So it's a patching of Herder-Schwenny graphs. Okay, so that's the model. So G is the graph. Okay. How's that described?
You probably want to say that by the regularity lemma every graph.
Right. So that's one of the things that made also the model these days attractive, is that, as Avi says, it seems like this is capturing something which is natural for large sequence of graphs. So in fact, some application or motivation. It's really, I think, one of the reasons why this model is popular is in fact the fact it came from multiple communities. So it is in
no pun intended.
no, but yeah. Ironically, it comes from it's for community detection. Is an application or clustering. That's where the name stochastic block model comes from. It's the machine learning statistic literature. These are generative models for a graph with clusters. And then if you are more in the random graph literature, so this would be called, Bolobash would call this inhomogeneous random graph. It's also related to what's called graphons. Graphon would be basically, it's a richer theory, it's a topological theory, but the limiting object of sequences of graphs are precisely an extension of block models where instead of having a discrete label for each node, you have a continuous label. So, and in algorithms or complexity theory, it's basically just blended partition model. And in fact, you can also model planted clique with it. Right? If you pick the matrix W to be just half, 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 and 1, and then you pick your P to be very tilted. It's two communities, and K by N for being in the clique, and 1 minus K by N to be outside, then this will be basically the planted clique model. And you can also do planted coloring. If you make the probability to connect inside the group to be 0, and say the same everywhere, that's the model that was discussed last week, the introduction of Feige-Stokes. Okay. So it somehow comes in the middle of multiple models. So a notation that I use also is symmetric stochastic block model of n, k, a, b. That just means that the p vector in the definition is 1 over k everywhere. So the prior is the same for every color, same size for the clusters. And then the W metric is going to be A on the diagonal and B everywhere else. In other words, you connect with the same probability inside any clusters and with the same across any pair of clusters. That's S for symmetric stochastic. So, okay, so now I'll define what is the problem we try to solve. The first thing we need is the notion of agreement. So if you have X and Y that are two vectors of length n that take the k colors as in their components, define the agreement between X and Y as the number of components that agree. Okay, you count how many times you have the same color in component I. Now, if you, especially in this symmetric model, you can see that there's a small problem with this definition, with the fact that there's no meaning to the colors in the symmetric case. You have two groups, you connect with probability A inside here and B across. You don't care who's called 0, who's called 1, or who has color blue or red. If you swap the color, it's completely invariant, the model. So because of that, the agreement is going to be always maximized over all permutation. So that's the permutation group on k elements. And here we're going to be able to take one of the vectors, relabel it, and that's actually the agreement matrix we're going to use. So because what we care about is to find the partition, not the actual colors. In many cases, if you have the partition, you can find the colors by just taking the size of the clusters or doing the low Flowers number by the edge density. But our problem is going to be to find the partition. So that's, yeah?
Why I, but I is in SK, not in SN.
Yeah, and Y is
Yeah. Yeah, pi is a color. Yeah. Right, just relabel the take you call this 0, 1. If you have a reconstruction that puts 1 everywhere here and 0 where here, you can flip the. Other questions?
Can you say what the model is again? What's SSBM?
SSBM is just a special case of the SBM where the P is uniform, so the groups have same size, and where the connectivity has the same value for any intra-cluster probabilities, and the same, it's a B for every pair of between any pair of communities. So that's just a shortcut notation for the SBM with these two parameters. Other questions? Okay, so that's, now that we have defined the agreement, we can talk about what it means to recover the clusters. So the general game will be we are given the graph only without the colors, without indication of anything, and you want to recover X. So the goal is to go from G to X. So we'll define two notions of recovery. There's going to be weak and exact recovery. We're going to say that weak exact recovery is solved, so that's just two different lines. I'm using a shortcut notation. Is solvable if there exists an algorithm that achieves with probability 1 minus O(n) of 1, so with high probability when the number of vertices tends to infinity, achieve an agreement of 1 if you do, 1 if you do exact recovery. So that means you want every vertex to be correctly labeled with high probability. And then here, we're just going to ask to do max of the pi plus some constant epsilon for some epsilon positive. So what is this? It's called a weak recovery because you just ask to beat what would be something you can always trivially achieve, that is to put everybody in the maximal size clusters. So that's something which gives you an agreement of max pi for free. So you want to beat by a constant epsilon this max pi. So these are the two extremes of the spectrum. The most demanding condition, every node has to be correctly labeled. And here is just beating what you would do with a random guess or with just using the prior. So that's what I will discuss today, those two extremal cases. Naturally, there's the in-between case that are interesting, but that's like the first.
But the PI, the P and W are known.
Yeah, so everything is going to be known P and W. And pretty much everything I'm going to tell you we can now do without knowing anything about P and W, assuming a block model. So I just simplified the task. You can estimate P and W. Any other questions on the setting?
Maybe just
Yeah.
can think of a different version maybe of weak recovery, where you're supposed to output clusters of the same size as the model suggests, and then even if you don't get the
Right.
element to be equal to the largest
Yeah.
cluster, you still did something non-trivial.
Right. So in fact, okay, let me make that comment because in the paper, one of the first things we do is to change the definition of weak recovery. That's not, in a sense, the best one to use. That's the easiest one to explain in a talk. So to save time, I went for this one. But actually, I think the most natural definition is even weaker than what you mentioned, without forcing the size, is to ask that you want to extract a set of vertices in your graph S such that at least for two community I and J, the number of vertices that you put from the first community in that set, the fraction is more than for the other group by a constant epsilon. So you want with high probability to be able to separate at least two communities. That's arguably the first time you can do something non-trivial about the block model. This is weaker than this, and you could also define something like what you mentioned, but that's like really the bottleneck, like the most basic condition you want to get is this. But it turns out when you ask for the symmetric block model, which is what I will discuss only today, to simplify, then all these are equivalent. That's why I don't discuss them. So in the symmetric block model, you really want to beat the random guess, right? If you have two groups that are roughly of size n/2, if you just flip a coin or put everybody in in one cluster, it gives you the same. It gives you roughly half by the law of large number, the agreement. I should normalize the agreement actually. So it's a number between 0 and 1. So you want to beat that half, that lucky guess. Okay, so the model is pretty old. So the statistic literature, this was from the 80s that they started looking at these models for clustering. Here and also in the 80s in the TCS community, Sipser et al., Bu, Bopana, they had papers on this planted partition model. But then somehow in the recent years, it came back in full power, in part due to this conjecture from 4 people, which are Dessel, Krashkala, Chris Moore, and Zdeborova. That was 2011. And Moore. The conjecture is about the symmetric block model. So symmetric block model K, and it was precisely for this weak detection setup. The exact recovery has been most studied from the 80s to late 90s. Most papers were on the exact recovery, also in the TCS community. And then in 2011, they made a very precise conjecture of what happens in the symmetric block model with K groups. And I'm putting the probability that you connect inside a cluster is going to be a constant by n, and the cross is going to be a different constant also by n. So this is the sparse regime where the degrees of the nodes in expectation are constant. So the conjecture says that weak recovery is efficiently solvable if and only if a minus b squared is more divided by k a. So they had a very precise expression for when this is possible with an if and only if statement. Further, they also conjecture that moreover, for k is more than 4, a plus k minus 1b and everything times k and then a minus b squared on top. We'll see in a second where this comes from, this expression comes from. But they say that for k is more than 4, then you can actually solve weak recovery below 1 for this ratio, but no longer efficiently, but with information theory. You understand what I mean by for information theory? It just means that if you allow yourself non-polynomial time algorithm, then even if this is below 1, you can still recover weakly the clusters.
Can't you do it for any constant?
Sorry?
Can't you do it for any constant information theoretically?
I missed the first part of the phrase. Can't you?
Can't you do it for any two constants? You said below, but I'm asking.
Yeah, you can always do it, but also below. Yeah. There's nothing. You can.
How below? Like you can do it for any two constants?
For any two constants? For you mean the a and b? Oh no, I'll discuss how far. I'll discuss how far how low you can go. Yeah. I'll discuss what's the information theoretic threshold like. But the point is that it's only at 4. For 2 and 3, this is tight. This is an if and only if. And also, if you ask for when is it solvable, then it's the same condition. And starting at 4, suddenly you have this region that appears where you can solve the problem, but we don't know how to do it efficiently.
Anyway, that's a conjecture. You didn't talk yet about results.
Yeah, that's a conjecture. So that we will prove that conjecture today.
But
Yeah, sorry.
But I guess what I asked, the answer is over there on the board, because I asked whether if a over n is a constant, b over n is a constant, and then this is like goes to infinity.
No, n goes to infinity. A is a constant and b is a constant.
No, but I asked.
Yeah.
A over n is a constant.
If A, oh, sorry, that was your question? If A and B, capital A and capital B are constant, then this is always, we can even solve exact recovery always, as long as it's not the same constant. Yeah. So that's going to be a very easy regime if you have that much intensity. Okay, so I'll tell you now the results. So the setting first is going to be the following. P is going to be n independent, so it doesn't scale with n. That means that the communities are of linear size, okay? Like think of 1 over k, the uniform case. And the number of communities is fixed too. But W is going to scale with n, and I'll always look at W that are of this form. There's going to be some intensity parameter that models the magnitude of the degrees of the nodes in the graph. And then there's this matrix Q. This is just a matrix in k by k, which is symmetric. And that's going to be a parameter. So this is n independent again. So what does it mean? It means that if you take a node that is in community I, okay? Let's say that this guy has, this is V with xV is I. He has n P1 candidate he can connect to. I mean, there's a -1 somewhere that I'm going to ignore. And then he has n P2 candidate he can connect to here and n Pk. And he picks here with probability Wi1, etc., Wik. So if you look at the expected number of friends you have in community, let's say J when you're in community I, is going to be precisely n Pj Wij. So if you build that matrix, which is n, so let's call capital P is diagonal little p. If you pick the matrix which is n capital P and W, which is the same as Sn, P, and Q, with this parameterization, that matrix is contained, that's a k by k matrix, okay? It doesn't scale with, the dimension is fixed. And if you look at the kth column in that matrix, let's say column I, this precisely contains the expected number of friends you have in each of the k communities. So I call this the community profile. So this matrix contains the community profile. Because it tells you if you are in community I and the expected number of friends you have is dictated by this column. So if you are in a different community, let's say I prime, then the more different these columns are, the easier it should be to separate these communities because they connect differently to the rest of the graph. So the question will be to understand what's the right metric of difference so that we can solve the problems that are mentioned there.
You're back in the non-symmetric.
Yeah, I'm back in non-symmetric case, yeah. So the point is, I want to state you the theorem in general, and then I'll do the proof in the special case of symmetry. So the theorem 1, so with Colin, says that if you are in the regime where Sn is log n, so now I'm putting myself with the regime so that these degrees, so that's the profile on how you connect in the intensities, but that's how it scales your degree. So it's going to scale logarithmically. So that's the regime, for example, where the graph is going to be connected if the parameters are high enough. If the average degree is more than 1, then by variance of Herder-Schwenny results, your graph is going to be connected, which we know we will need connectivity to solve exact recovery. To ask that everybody is correctly labeled, if you have an isolated node, you don't know what to do with it. So you already failed that node with property 1 over k or 1 minus 1 over k, so you cannot solve exact recovery. So we need to be here for exact recovery. And then the result says that exact recovery is efficiently solvable if and only if the minimum between I and j in k, they are not the same, of some function d plus that I'll define in a second. This is more than 1. Okay, so what is this d plus function? So I'm basically looking at some distance between those columns. And if they are far apart, if any pair of columns in that matrix is far apart with the metric d plus, and far apart means more than 1, then you can solve exact recovery, and d plus is like that. So you have a maximization for a parameter between 0 and 1, sum over all the components in k. So this is just vector of dimension k, x and y. It's going to be our columns of the matrix. And this is going to be the arithmetic mixture that you have between the component of x and y minus the geometric mixture. Okay, so that's not a distance. It's what's called, this is an F divergence. It's a family of functions that have certain properties. I'll skip the details, but for example, the KL, the relative entropy or Kullback-Leiber divergence is part of this family. And somehow it's not too surprising that it's an F divergence shows up. It's because it's going to be the result of the analysis of some rare events. And in fact, F divergences have a bunch of natural properties, like if you merge communities, it should be easier to recover the merged communities. If you drop the edges, it should be harder. So all these things are reflected into natural properties of these functionals, but it's not a distance. It's not symmetric, this guy, and it's not satisfying the triangular inequality. So I think lots of results were trying to prove a result of this kind for the L1 norm, because the L1 norm is what comes up for connectivity. And the surprise is that it's a different object.
But if and only if means the efficiently solvable if and only if
right.
means that if it's greater than 1, you have an efficient algorithm, and if not,
right.
there is no,
yeah.
you cannot distinguish.
So the reason why we can have,
right.
The reason why we can have an if and only if statement here is precisely because if you're below, then information theoretically is not possible to solve exact recovery. So.
Why do you say information theory? What
it means.
Information theory have to do with this?
Well, that's
you
what.
have enough information to
I mean, that's a classical reaction that I had when you had some training in information theory. First time you hear it, you're surprised, but I think it makes complete sense. It just means that there's enough information in the graph to recover the clusters. It doesn't mean that we use Shannon's equations. It just means that it's based on the information that the graph tells you about the clusters.
The word information theory has a specific meaning, right?
Well,
It's not
that's.
just theory and information, right? These two words.
I mean,
So-
okay, it's not. It doesn't mean Shannon theoretically. It just means it in terms of the. You could form it in terms of entropy if you wish. The entropy in the graph in the clusters given the graph is actually not going to 1. 1 because of the symmetry. It's not going to 0 if you wish.
It means that we
But-
are not limited computation.
But yes,
Yeah,
we.
but information theory is not the only theory where you don't put a priori computational
Yes, there
limits.
is computation and the rest of the world is information theory.
I'm happy with that.
Okay. So some comments. The complexity of the algorithm is O(n) log n, so it's truly efficient. I'll discuss it a bit. Also, the name we call this a CH divergence. It's a generalization of the Chernoff and Ellinger divergence. If you plug half, so if you have in the symmetric case, the maximizer here is precisely at half by symmetry. What this needs to be checked. And then this becomes exactly the L1 norm between the square root of the x and y. And this is called the Ellinger divergence. That's why it's a generalization of Ellinger. It's a mixture between those two objects. Now, to connect to the talk of last week by Uri, if you plug, if you are in the symmetric case and you plug a is equal 0, and you call b to be b log n by n, right? That's our regime. Then this says that if b is more than k, in fact, let me ignore what happens at the threshold. When I say if and only if, I'm kind of avoiding the discussion of the threshold. It depends a bit on some case. We have the complete picture, but don't point me about what's happening at the threshold. There are cases to distinguish. But if b is more than k, then there's a unique, you can recover the plenty coloring. Hence, you can color the graph efficiently. But it's not necessary to recover the plenty coloring to color it. So now the second result is for this was still with Colin. This is not the same paper. This was in Fox, and this was December, and this one is no, this was January, beginning of the year, and this one is a different paper at the end in December. So the result is for now a weak recovery. So there's two parts. So it's efficiently solvable. Of course, you see that's a if now, not if and only if. But the general functional is this now. Lambda I of PQ are the eigenvalue in order of increasing. So lambda 1 is the largest, then lambda 2 is the second largest in magnitude, etc. So you take this matrix PQ. So now we are, I should mention, now Sn is 1. In other words, the intensity is constant. It doesn't matter what constant you take, and because we have this constant matrix Q. But that's the constant degree regime now. So in that case, you can solve recovery efficiently if the ratio between the square of the second largest eigenvalue of the matrix by the first is more than 1. And this reads exactly as so the largest eigenvalue in the symmetric case is this. And no, sorry, that's the second largest. The first is this. So if you do that ratio, it's precisely the term of the conjecture. So it does settle the conjecture. That's for symmetric. I'll also tell you the conjecture was already proved for k is equal to 2. I'll mention what was known right after I extend the theorems. And then B, so this is conjecture to be tight. So we believe that if this is below 1, even or equal to 1, then you cannot solve this sufficiently.
There is some factor of 4 from the Ramanujan bound, right?
Right.
Is,
I mean, I don't see the 4, no? Why 4?
because it's in a direct, well, if the average degree was D, I guess. Anyway, if the average degree was D, you expect the first eigenvalue to be D, and then the second cannot be smaller than 2 square root of D.
Right, yeah.
Right, so this ratio would be.
Yes, yeah. Yeah, that's because of the non-regularity.
Yeah, so there's a
Yeah.
gap. I mean, maybe
But-
you can go down up to 1 quarter potentially. I mean, if this is
Yeah, but we'll see. I'll try to, if at the end, I'll try to connect again to a Ramanujan graph because. Okay, I'll state the theorem and I'll make a few comments on that. B, if we can detect if k is in fact more than 4, as it was conjecture, then there exists some P and Q, and in fact it's going to be the symmetric block model, so the same as this, such that weak recovery is solvable. Information theoretically, or just with an algorithm which is exponential time, running time, if this quantity, which I call the SNR, the signal to noise ratio, is less than 1, it's below 1. So basically this is not tight if you are 4 communities, but so they have argument in the paper of Dessel that to argue that this is in fact tight based on the replica symmetry breaking type of arguments. And my belief at this point would be that this is in fact tight. I don't see a reason why not. But I think with unless
for the efficient case.
for the efficient part, yeah.
No, but I don't understand. You cannot distinguish the efficient and the non-efficient case with the technology today.
No, that's what I'm saying. Unless P is in there's progress on P and P.
So this is what you mean.
Yeah.
You mean
Right.
condition on some
Yeah.
complexity.
I think we have sort of one algorithm in mind, and they show that algorithm will fail.
Yeah, so the replica symmetry breaking, all these things are also saying basically that Billy's propagation is going to fail. BP is going to fail if this is below 1. It doesn't mean, so it's not.
You have a
Yeah.
result there where
But that's not efficient. Yeah, so that's going to be another argument. But if you believe the physicist approach, then they have heuristics, not based on reduction to
there's no reason. Can you state again what you believe is the truth?
that this is in fact necessary for efficient algorithm. That this is necessary.
So you mean if somebody finds
that the Billy propagation is the best algorithm.
Yeah.
that's what you believe?
Yeah. I don't just have another reason to see why not. Yeah, at this point, based on the work we've done. So now I can also, yeah, I can tell you also how big is that gap. So let's take the coloring problem. So A is 0. So you don't connect between the clusters. So then when can you detect that planted coloring? So this bound, the efficient bound, is going to read. So part A reads B has to be more than K times K minus 1. So like K squared roughly. Whereas the bound that we have from part B reads like B is more than up to a constant K log K. So basically from linear roughly to quadratic. So it's a huge gap between. If your intensity B, if you connect with B by N across cluster and you're roughly above K log K, then you can detect with exponential time method. And the method is just sampling a clustering which has typical size volumes for the clusters. And here you're stuck at K squared.
Because here it's really not a source detection, right? Because I think detection is.
Yeah, detection is weak recovery are the synonyms. Weak recovery or detection is the same.
No, I think you can detect the. Okay. Let's see. Okay, I guess it. Okay. It depends a bit what you mean by detection. If you mean detection, distinguish this like a planted instance from a random instance. I think that is easier than.
Yeah, so if you want to say, is this graph a block model or an heterogeneity graph, I think it will also be this, the condition. Sorry, it will also be reading like this.
The information, but
Yeah.
There's some cycle counting that goes beyond the.
Not beyond this, yes, but not beyond this. I think the information sharing argument is actually more than cycle counting. Yeah. Okay.
It's like the situation in I don't know.
Planted click.
Or SAT.
Yeah, or SAT.
There is a gap between
Right.
what and
Yes. Yeah. Exactly. Yeah. I mean, the good news in a sense, it's a planted model. It's not like SAT, which is unplanted. So that's why we can say that's not why, but the good news is we can be more precise now. For example, we have the threshold here as opposed to SAT, which is still unknown for 3 SAT. So there's a bit more we can say.
No, I think there are conjectures of the same type also in the soft case.
Yes. Yeah. Yeah. The gap in terms of gap. Yeah.
The best
Right.
algorithm is belief propagation.
Yeah.
You can solve it,
Right.
I don't know, like a condensation.
Yeah. It's a similar type of behavior. Yeah. Exactly.
Here, do you always get the quasi-poly algorithm for free?
Here is still n log n. Yeah. This is O n log n. The algorithm we have, and it's going to be a linearization of BP.
No, but can you get even up to the threshold? Can you get an n to the log n algorithm?
Yeah. You mean this threshold? Both.
For B. For B, you're asking?
Yeah.
For B.
So this is different from SAT, where
Oh, I see. So no, for B, it's exponential time, the algorithm to succeed below 1.
you see you can.
I didn't try to see if we can get something in B, like how
So
big.
If I give you, well, I guess k is not a constant. How?
K is constant. K is constant. Yeah.
So if I give you log n seeds in every cluster, that's not
The graph
enough.
is sparse. So it's,
Yeah,
Yeah.
relative edges between them.
Oh,
Yeah.
it's very sparse.
So yeah, it's constant degree.
Constant degree for weak. So there's always 2 parts. This is log n degree theorem 1, constant degree theorem 2. Here you recover every node. Here you just beat the random guess. Okay, so I'll just tell you. There's 3 ideas I wanted to tell you. The third one we already dropped for sure. It was how to cross here. I think it's maybe a different theme, but at least there's 2 things I think that are general concept that can be used.
Question about B.
Yeah.
In that case, let's say this regime, would there be, like, if I take an arbitrary legal K coloring of the graph, would it necessarily be correlated with the planting? Information theoretically.
Well, the thing is, if B is tiny, you can still color easily, right? The graph is disconnect. It's like a bunch of trees.
When B is larger than
Oh, I see. Oh, I see. Yeah.
like that,
Okay.
they-
Yeah. So basically,
just to be K
so
colored.
that's the class project of which I put of NAM. Is like can you go from a reduction from this to coloring now? That's a question we're looking. Yeah. I'll be happy to talk with you if you want after. Yeah. Okay. So let's see. Maybe some comments. So the gap is big. I mentioned the complexity. Also, if you want to use the chromatic number of Erdős-Rényi, that's what kind of your question. You can also ask when can you color Erdős-Rényi with K colors. So if you use the Acleoptas bound, you don't cross at 4. Now Acleoptas, you cross at 5. If you could do a reduction to that. So basically, it takes a bit of work to cross at 4, the least value. But now I'll skip that part and I'll just tell you 2 things. So. First thing I'll tell you is about local to global amplification. And then linearization of BP, which is equivalent to spectral. Yes, BP is belief propagation. And when you linearize BP, so maybe you don't see what this means, but BP is what is everybody is going to have a belief of who you are at the beginning. So everybody flips a coin. Let's say you have 2 groups. We are in the symmetric case. There's roughly n over 2 nodes here and here. You connect with A by n inside the groups and B by n across the groups. We don't know where the partition is, so let's all flip a coin for blue or red. And now I'm going to look at my neighbors, and my neighbors tell me, oh, I'm blue, I'm red. And then I just do an update of who I should be based on the distribution of the graph locally, like a Bayes rule. So instead of doing this using Bayes rule, what if your belief at the beginning is roughly half? But OK, so instead of thinking of the belief to be exactly half, by the central limit theorem, there's going to be roughly root n nodes that are going to be either on the right side. So if this was the truth, and if you do your random drawing, so that's the truth, and you did that. You did this was blue, and the other one is red. That's the random guess. Just by the central limit theorem, you have root n nodes that are going to be on the wrong or the right side, right? It must be. You're not exactly 50-50.
The wrong is right.
And the wrong is right because you don't care the colors. So in other words, you can do like a simple coupling argument. You could basically work with the same model where every node has a guess which is not half, which is half plus epsilon by you basically have a bias of 1 over root n towards the true communities. So now the question is that if you linearize the belief propagation equations with the fact that you're very close to half for your original belief, and you only work out the Taylor expansion of order 1 for epsilon, then running BP is equivalent to using a power iteration on some operator, because it's a linear transformation now. Power iteration means what? Means you take your original guess and then you apply a matrix iteratively. That's going to be the same to iterate those message passing type of interaction. So that's high level, but basically that gives rise to a new operator, which is what we call the RNB operator, which was also defined. Oh, I should tell you the prior work at least, which was also defined by Bordenave et al. And this operator is basically is no longer the adjacency matrix.
Why don't you write it? I mean,
Yeah, I'll do this now. Yeah. Okay, so that I think is. So I'm basically starting with 2, and we'll see, I guess, if there will be time for 1. So I'll just write the operator for now, and I'll tell you what's happening. So before that, what would be the naive things to do if you want to detect the communities? So you look at the adjacency matrix of the graph, okay, adj. In expectation, if you take the expectation of this matrix, and if I order my nodes to be in the same group at the beginning, this matrix will look like that. A by n everywhere here, A by n everywhere here, and B by n, D by n. In expectation, right? That's this constant blocks here. I'm putting all the nodes in group 1 here and group 2 here. So if you are lucky that you could work with this matrix, even if you don't have the right order, the right permutation, if I apply a random permutation on this matrix, but the eigenvalues are going to be what? The first one is A plus B by 2 with the all 1 vector, right? If I plug all 1 here, I get this eigenvalue. And the second one is A minus B by 2 with 1 on the first communities and minus 1 on the second community. And then I have the span of the orthogonal space to these two guys with eigenvalue 0 of multiplicity n minus 2. So this guy we're not interested in getting. Yeah?
Just to clarify, you actually have them connected to themselves. There's no 0 on the diagonal here.
Yeah, there should be 0, but I can put a loop. Let's say we do the model where we add loops. Otherwise, there should be 0 on the diagonal, which is only going to shift the eigenvalues. So let's do the model with loops. So now, here, this is something we don't care about. It's just the average degree. But if you had the luxury to work with the expected graph, which you never can, then you just look for the second eigenvalue and take the eigenvector and then say positive first community, negative second community. So that fails because of the fact that if you write your true adjacency matrix as a perturbation of your right, if you look at it as a perturbation of this matrix, the noise is going to be have fluctuation that completely disrupt the ordering of these eigenvectors. And this is a classical issue of high degree nodes. When you are in the constant degree regime, there's going to be nodes that have logarithmic degree, and so they have super high degree. And this is the guys who are going to catch the dominant eigenvalues. So if you are in the logarithmic degree regime, you can do a trick that is now well known, and I think Feigehoff also uses this, is you trim the high degree nodes to regularize the spectrum. And this doesn't quite suffice, or I don't think yet it's shown that this works to get the threshold, but at least if you do another trick at the end, which is you improve again locally at the end, then you can get somehow the threshold. So it's even for logarithmic trimming is not trivial, but here trimming fails. If you just take the adjacency matrix, trim the high degree nodes, you're far from getting the threshold. So in a nutshell, what the non-backtracking operators does is it sort of leaves, instead of using the adjacency matrix, define this other matrix B. Okay, so W. It's a matrix of size 2. So I'll first tell you the definition with the 2 non-backtracking matrix. So R is a parameter which is an integer, so I'll define 2 and B. So it's the dimension of the matrix is going to be 2 times the number of edges cross 2 times the number of edges. So you order your matrix with no longer the number of vertices, but with twice the number of edges, because what you do is for each edge you have in your graph, you're going to replace it by 2 edges with the 2 directions. Okay. Each edge duplicate 2 directions. And now I'm going to put for WEF, so E, F are now, this is let's say EF. This is an index for edge E and edge F. So let's say that this is E here. That's my E, and this is my F. So this guy is going to be 1 if F follows E, like I drew in this picture. And it's going to be 0 if either they are disjoint or if F were to come back and to loop back here. That still makes you a 0 entry. So that's a binary matrix of dimension 2 times the number of edges. And if you do the R non-backtracking operator, it's just the extension of that, where now the dimension of the matrix is going to be 2ER times 2ER. Sorry, just ER times ER, where ER is a number, is all the set of R paths in G. And now you connect 2 paths if you have this picture that looks like that. That's the path E. That's for R is equal to 3, for example. And that's the path F. It follows again the path. So if the paths follow each other without looping back, you're not allowed to loop back. Put a 1, otherwise put a 0. So what the algorithm to prove is basically, if you use this matrix for R, which is constant, then the second eigenvector gives you the communities.
So you use what do you do exactly? What is the vector you apply this matrix to? You have to start this one.
So there's a shorter and a longer story. The longer story is that we implement this in a power iteration fashion because we.
When you apply this, so there's a new matrix that's defined
Right.
by the graph. What
Yeah.
vector? What initial?
A random vector. And you
random
iterate.
vector. It's not like a random color and then extended to the.
It's actually this. You can do both, but that's fine. Yeah.
Sorry.
I keep trying to no, that's exactly what it is. You take a random coloring and then you apply it to, so you define xv to be random, and then every edge that starts at xv here gets that color as an initialization for the path where you start. And then, but what the reason why I started by saying there's 2 story, you don't have to apply it to a vector. You can just do it brute force by extraction of eigenvector if you prefer. That's the way we do it for the proof, right?
Logarithmic power of this matrix.
Yeah, exactly.
And then you look at the first eigenvector of this.
Second,
Eigenvector
yeah.
of this, and that
Yeah.
will be this will be a function on paths. And now you have to what will be. The
Then you just do a majority vote at the end. All the paths that end up in your node here, you count how many guys are blue or red, and you declare to be committee 1 or 2. But the idea at the higher level is just that this operator is somehow doing the job of regularizing the spectrum. it has W, even for 2, in fact. We don't have the proof for 2, but we believe it's true for 2 also. Actually, for 2 community, this was proved by Bordenave et al. But it doesn't work for more than as soon as you have 3 communities. But if you have more than 2 communities, then you take a constant R, then it works always. But basically, the second eigenvector of this guy, so second eigenvalue, you compute it, you look at the eigenvector corresponding, you round it positive, negative, and this gives you the communities. Yeah.
Now this is not a symmetric matrix.
No, it's not.
Okay.
But you still have, it still have some symmetry, but it's not a symmetric matrix. Yeah. So yeah, so the story is I think R is equal to 2 always works, somehow luckily, but it turns out that taking larger R is also, I think, something that you want to do often, even if you use that matrix. So like a student did a master thesis and implemented this on real graphs, and the larger you can afford R, which increases a bit your complexity, the more robust you are to triangles or things like that. For example, if you take R is equal to 2, you can take an adversary that puts some bad triangles inside a cluster that makes it fail. Whereas if you avoid cycles, so the idea of using this is that you're not counting the walks that cycle around the loops of size R, then you're a little bit more robust. So it's basically the larger R you can afford, the better, but the complexity increases. But if you just want to beat to detect here, R is equal to 2, I think is going to work, and it's probably possible to even prove it for any K. It was done for 2 groups by Bordenave.
What does this graph do for planted click?
So for planted click, you are no longer in the case where P is n-independent, right? You have this tiny community now.
But you could still
use that.
this graph, the spectral gap below.
I think it cannot beat the Montanari 1 over Rudy bound, because this is a linearization of BP in a sense. So that's the part that probably I won't be able to explain, is how you can view this operator as just linearizing BP. But basically, because the Montanari's paper already uses BP itself, I doubt you could improve on BP with that.
Also, if the graph is regular, then this non-backtracking random walk matrices, like the eigenvectors are very closely related to the eigenvectors of the adjacency matrix.
Yeah.
One from there.
So you can I think you can express the Ramanujan graph in terms of non-backtracking operators by saying that there's no eigenvalues between the Perron-Frobenius eigenvalue in this region. If this is the Perron-Frobenius eigenvalue, the largest, because it's not a symmetric matrix, but the largest eigenvalue of largest magnitude eigenvalue, there's no eigenvalue inside here. This is for regular graph. This is exactly the same as Ramanujan graph. So what we are saying here is that if you have not a regular graph, but you have an Erdős-Rényi type of graph, then the adjacency doesn't have this kind of nice behavior, but this operator still has this kind of nice behavior.
But I'm just saying that it seems to be useful to look at this matrix sort of only if the issue in your computational problem is due to non-regularity.
Right, if you don't have degrees that are constant, yeah.
And for planted click, it's not like this issue whether you are regular or not. It doesn't seem to be that important for planted or.
I see. I mean, I don't think you will. As I said, I don't think you will beat the current state of the art for planted click. Where you could actually do something is if you do an interpolation between planted click and the block model. Eventually, I think this will be interesting if you do a relaxed problem. So I guess in maybe 5 minutes, I can either see what. I can just tell you very briefly in 5 minutes what is this local to global.
You can take 10 if you want.
I see. But I think it now is the trade-off. But I think what's important is that this is there's something maybe I think I'll have to give up the local and just tell you what's happening about the amplification, because it's basically not a local algorithm. The number of iteration, the power we have to take goes beyond what you would do to have just a local algorithm. In other words, you're not running BP only on tree-like graphs. You have to go down to the cycle regime. If you take still logarithmic. But if you take a node in your graph, you know that locally it's like a tree, right? So I mean, for some time, for some depths, it's going to be like a tree. You have Poisson A by 2 neighbors in the same group and Poisson B by 2 neighbors in the second group at depth 1. And this keeps going. You still have a tree up to a depth t, which is going to be log n by log the degree times half minus epsilon below that. That's just the birthday paradox. If you have more than that, you have more than root-n children, and then you have collusion between two nodes. But if you're below that, you have less than root-n children, and then you have a birthday paradox. It doesn't kick in. If someone tells you the value of these leaves, exactly, then you can recover the root with better than half, as long as you have this condition which is satisfied. The condition of the theorem. And this was proved, by the way, all this was done by Mossel, Niemann, Sly, and Massoulier for two groups. The problem is that you don't have the value of the leaves, right? So we have that guess, which is a little bit better than half, where epsilon is roughly root n. So you can ask, when is it that I can amplify such a naive guess to something which is better than half here? If you do the back of the envelope computation, you see that the depth of your tree is not even in the regime where it's not tree-like, but it has to be actually more than this, more than the number of nodes you have in the graph, more than the diameter. So that's why you cannot just count voting based on the shortest path, but you have to start doing walks. You have to start going, you go to the den of the diameter of the graph, and you start bouncing back and counting how many walks start in a blue or red nodes and end up to my root. The problem is that if you just do naive walks, this is going to be chunks, but it's efficiently computable. If you want to count how many paths start in a blue or red nodes and end up here, then this is good. It's going to work, I think, but it's not efficiently. I mean, it's going to be polytime maybe, but large polynomials. So the non-backtracking walks are, in a sense, the win-win. They give you faithful statistics to decide about the roots, and they are efficiently computable. But the reason why it's hard is because you have to go to very large depths where you have cycles and all sorts of things. It's not a tree-like computation.
So what's the nature of the analysis then?
So basically, you
Because you cannot assume it's a tree. So
yeah. So you still have to do. It's a lot of surgery. You count how many non-backtracking walks, and you have to center them because you want the second eigenvector at each time. So there's a nice way to write non-backtracking walks iteratively. The number of walks that end up in the edge v prime at times t is going to be the sum of the number of walks at times t minus 1 that end up in v prime from v double prime, where all v double prime is not v, but there is an edge between v prime and v. So basically you have a recursion for saying if at time t you completed those, then you can augment to the next step. So that is going to be a recursive way of completing non-backtracking walks. You have to subtract them to center them, and then you have to show that despite the fact that there is these other cycles, the count is still correlated with the truth. So it's not something that takes a few minutes.
so cycles don't enter the argument really.
Luckily not at the end. They don't disrupt your. You have to handle them, but they don't disrupt your plan. Yeah. They don't change the outcome. It behaves essentially. They don't hurt you to the fact that you can still detect when. So what is this quantity here? The intuition between this quantity is simply the signal-to-noise ratio between the expected counts of blues and reds versus the variations of what you have between those blues and reds. And I think that this is more than one. Say that you can distinguish the two counts. The variance doesn't swap things around. Okay, so I don't know if I can just tell you what is the local global in 5 minutes or stop. Yeah. So for exact recovery, there's something which is, if you're familiar with the connectivity in Erdős-Rényi, there's something which is happening here again. In the Erdős-Rényi graph, connectivity is equivalent to the presence of the disappearance of isolated vertices, which is not obvious, right? If you have isolated vertices, then you must be disconnected. But the fact that the equivalent is just because of their Erdős-Rényi nature. So here there's something again similar. If you call P local, the probability that you fail at recovering one node, so you want to recover x1 node, and you are allowed to do the maximum likelihood operator when you have the entire graph and you have everybody else. So what is this quantity? Is I'm just asking, you have to guess a single node. You write your two groups. I tell you the answer. I tell you everybody, this notation means everybody but node 1. So here you have the answer. You pick one node in the middle. I hide where it came from, that node. I don't tell you. And I ask you, can you classify where that node belongs from by looking at the graph and the colors of the other nodes? So that's a local problem. And you will have some probability of error for this local problem. It's going to be vanishing most of the time, but the question is the scaling. So if you call this the local probability of error and you call global the probability that you fail at recovering the entire guy in one shot. So now there's no genie that gives you some nodes, but you have everybody to recover the original problem. Then what we show is essentially that in the logarithmic degree regime that there is in the theorem 1, P global is going to go to either 0 if P local is less than 1 over n, otherwise 1 if P local. You fail globally if locally you fail with more than 1 over n. That's like, imagine you have n coins and they have probability 1 over n. That's exactly the threshold for when one of the coin goes ahead. So what's happening is, I think this is this is more general. That's what we try to do now. We are writing that theorem in a much more general context where it has nothing to do with the block model. It's just as long as you have some sparsity in your model and some symmetry, you get something that behaves like that. What's more specific to the block model is that when you analyze P local, now you're doing something which is easier than the original problem because you're only looking at a one node problem. So by using large deviation, in the block model, this will be n to the minus this d plus function that shows up here plus little of 1. So that's why you have this threshold at d plus being more or less than 1, because the probability of error scales polynomially. So this more or less than 1 tells you when you have these two conditions. If you work with another problem, the large deviation analysis is going to give you another exponent, and there's going to be another fundamental limit, like in the Shannon's model. But I think this is just asking some sparsity in the graph. You don't want to have degrees that are constant, like your question. That doesn't work. Constant degrees. Constant edge probability, that doesn't apply. But as long as you have a degree which is sublinear, and you have some symmetry, then you have a result that is of this kind. I don't know exactly. There's going to be some aspects that are a bit technical, but I think there's something much more general.
You know that this kind is the information theoretic sense? Or
Yeah. Okay, so that's going to be information theoretic. Now, the good news is the way you make this computationally also, that's the reduction, is that you start with a graph, and you're going to do this, you're going to split your, you're going to throw every edge from your graph into a first copy and put the complement in a second copy. So you have the graph here, G at the beginning. Subsample first copy G1 by putting with probability gamma every edge and put the complement here. So if the degree was logarithmic here in n, I'm going to put this gamma to be, let's say, for example, log n by log n. So that the degree here is log n. That's my gamma. Now, if you can solve the problem here to get something which is approximately good, so it's not going to be exact, but it's going to be roughly, most of the nodes are going to be correctly colored, then you can just look at this as being your new problem with, again, log n degree, because this is vanishing things. So now it's basically, you have this, you emulate this genie that gives you the answer from this copy. And now you can just clean up the graph from this copy, and this is going to be efficient for free. So this is as long as you can solve this efficiently, this is built in to be an efficient threshold. The question is, when can you solve this efficiently? And that's why this problem there's no gap, whereas there's the gap of detection is because you still try to here you can show that this is like detecting the clusters with a degree which is increasing. So every region where there could be a gap, you will pass it because the signal is going to be growing as opposed to constant. And that's basically why. So this reduction, you can make it efficient and not just information theoretic. But basically, that's the game. The game is each problem you're given, you can reduce it by doing these graph splitting techniques up to the level you reach a bottleneck problem for which you can no longer reduce. And what is that bottleneck? Is detection. And if you can get there with diverging degrees, then you're done. You can amplify everything. But if you are a constant degree like in detection, then it's tight.
I guess the question period already. So any more questions?
So if you ask about what's the fraction of, so in the path recovery regime, if you ask about what's the fraction of the nodes that you can recover for arbitrary Q?
Right. So that's a hard problem. So for two groups only, it's not known yet. We have studied this in fact with a student at Princeton, and we have a conjecture. We're pretty sure it's the answer. Right now it's only an upper bound, but it's going to be a function of the fixed point on the problem of recovering the root from the trees. If you have this, if you use it as a black box, when can you in a tree problem guess the root from seeing the leaves? If you take that distribution, which is you cannot express it explicitly, it's a fixed point equation. You can use that to express the fraction of nodes. There's a paper, Moser and Iman-Sly show that this is tight for large SNR. But for the constant SNR regime, it's still not fully done, yeah. And if you don't, that's for two groups. If you go to key groups, I think it's going to be hard to solve this problem. But we all know what to do, by the way. If you want to achieve that optimal fraction, you run this thing to just get a better than 50% guess, and then you run BP. Because if you run BP with a good initial guess, then it's going to be optimal. So we know how to achieve the optimal fraction. Trusting BP is optimal. But we just don't know how to find the expression, how to prove that this is the expression.
So you're saying that let's say if you have two groups and you wanted the correct fraction.
If you want the correct fraction, you do a two-stage algorithm. You run what we have here to detect. That gives you a plenary classification. Now you use that as what you feed into a classical BP.
But then you can prove that if you feed into BP some rough guesses, that it will give you.
But it's not rough guesses because it's been amplified by the first stage.
Yes.
So then you can prove, I think, that this you already put yourself in a good guess. Then this will actually enhance the accuracy. It's very hard to prove that BP with a random guess works. That's why we do this whole thing. This is a linearization of BP. We can analyze it, and this works. Now we have this, plug the result in BP with a better than random guess, and then you can again, I think. I mean, when I say it works, it still requires some. But Colin, for example, I think is the kind of student who would know how to do it fairly quick.
Thanks.
Thanks.